Welcome to Unit 2. This is very exciting. We're finally at derivatives. In this unit, we're going to start by using the limit formula to find derivatives, and then we'll move on from there. Welcome to Calculus 1. This is your first major topic in calculus. Congratulations. Here we arrive at the derivative of a function. We've already learned that f prime of c is the derivative, and this formula, the limit as x goes to c of f of x minus f of c over x minus c, is how we've been finding the derivative. I'm going to show that these two formulas are equivalent, where the limit as h goes to 0 of f of c plus h minus f of c over h. These are equivalent formulas, and sometimes it's more convenient to use the first formula when we're given a specific point, and to use the second formula when we're not given a specific point. Generally, we see that that's how those become valuable, these two equations, this one or this one, but you're welcome to use either equation at any time. There isn't really a right or wrong answer about when you use which equation. It's what you feel most comfortable with. We also have this graphic in the corner that shows they really are equivalent. H is the distance between the first point you're given and the second point. So as h gets really small, or in the case of the pictures we were looking at before, as the red dots got closer to each other, we're going to get a more close approximation of the slope of the tangent line. And whether that includes taking the limit as x goes to c or the limit as h goes to 0, we're going to get the same answer, because as we will see in 1 minute, these are equivalent equations. To start, I'm going to take this f of x minus f of c all over x minus c, and we're going to substitute in c plus h for x. So f of c plus h minus f of c all over c plus h minus c. Now, in the denominator, I can see that my c's will cancel because I have f of c plus h minus f of c all over c plus h minus c, and my two c's will go away, one positive and one negative, and I come to the equation of f of c plus h minus f of c all over h. And instead of taking the limit as x goes to c, now I'm going to take the limit as h goes to 0. Now in example 1 on page 173, we get to demonstrate this equation using a different problem. Now notice this question is asking us to find the derivative of a function f of x equals x squared minus 5x at any real number c. Usually, the first ones were asking us to find it at a specific number, a point like x equals 3 or x equals 2. Again, when we have any real number, this other equation is just generally more conducive. Now, there are a lot of pieces to this equation. The first piece we see is f of x plus h. The next piece we see is f of c. So I'm going to rewrite my function as c plus h and c. So let's start with f of c plus h. So everywhere I see an x, I'm going to plug in a c plus h. So c plus h squared minus 5 times c plus h. So I'll multiply that out, and I get x squared plus 2ch plus h squared minus 5c minus 5h. I'll do the same thing for f of c, just to substitute it in, so I have each piece before I go and try and solve the whole equation. That's going to be c squared minus 5c. Now I'm going to substitute into the equation the limit as h goes to 0, and I'm going to be using this equation that we just simplified, and then minus that one. So c squared plus 2ch plus h squared minus 5c minus 5h minus c squared minus 5c all over h. The limit as h goes to 0, and let's simplify this by distributing that minus sign to each piece. C squared plus 2ch plus h squared minus 5c minus 5h minus c squared plus 5c all over h. So the c squareds will cancel, and then we have a minus 5c and a plus 5c, and those will also cancel. So I'm left with the limit as h goes to 0 of 2ch plus h squared minus 5h all over h. And now I see that I can factor an h out of the numerator. I have an h in each spot. I have an h here, an h squared here, and an h here. So we have the limit as h goes to 0 of h times 2c plus h minus 5 all over h. This is a hint. Whenever you do this type of a problem, you always have to be able to factor the h out. Otherwise, we're going to get an indeterminate term of 0 over 0. So if I get to this point and I haven't been able to factor an h out so that I can cancel my denominator, I probably made a mistake. Maybe you forgot to distribute the negative sign, or maybe you FOILed incorrectly, or some other arithmetic mistake is probably made. But let's get back to the problem. Now I can cancel the h's, and I'm left with the limit as h goes to 0 of 2c plus h minus 5. Now I'll plug in h goes to 0. So I'm going to replace the h with a 0, and I'm left with 2c minus 5. So my derivative for any f prime of c is 2c minus 5. I also want to say here that there's no reason to use c instead of x, except for the book does as an example. But you'll see in our next problem that we use x, and that's totally fine. Now this is a really important point. The derivative of a function f prime of a function f is f prime of x equals the limit as h goes to 0 of f of x plus h minus f of x all over h. So as I said, this is the same as the limit formula that we've been using before, but this gives us a much more broad answer for any x and not just at a specific point. So the limit exists if the derivative is said to be differentiable. So if the derivative exists, then the function is differentiable. These are just one and the same: derivative, differentiable. They're like the adjective and the noun form of the same word. So if the function is said to be differentiable, then a derivative exists. Example 2 on page 173 asks us to find the derivative of f of x equals the square root of x, and then determine the domain of f prime. So again, first we're going to use the formula, the limit as h goes to 0 of f of x plus h minus f of x all over h. If you want to continue to use the c, you can. I find it a little easier to just use x's, but whatever you want. And the first thing I like to do is to write out f of x plus h. That's the square root of x plus h. Now let's plug it into our limit formula. The limit as h goes to 0 of the square root of x plus h minus the square root of x all over h. Now hopefully remember that when I have these square roots, and when I plug in 0, I'm going to get my indeterminate form. My next step is to multiply by the conjugate. And in this case, we're going to multiply by the conjugate of the numerator, which is the square root of x plus h plus the square root of x. All over, the same thing, square root of x plus h, plus root x. And when I FOIL the numerator, I have the difference of perfect squares, so I just get the limit as h goes to 0 of x plus h minus x all over h times the square root of x plus h plus the square root of x. Now my x minus x in my numerator will cancel. I have the limit as h goes to 0 of h over h times the square root of x plus h plus the square root of x. Again, once I get to this point, I need to be able to cancel my h's out. If I can't cancel my h's out, then I've done something wrong. And usually the something wrong is multiplying incorrectly, forgetting to distribute a negative sign. I know I sound like a broken record, but it's really frustrating when you do make these mistakes. So I just want to give you a heads up. So we'll cancel our h's here, and we get the limit as h goes to 0 of 1 over the square root of x plus h plus the square root of x. And we'll plug in h goes to 0. So that's going to be 1 over the square root of x plus the square root of x, or 1 over 2 square roots of x. Example 3 on page 174 says the surface area S in square meters of a balloon is expanding as the function of time t in seconds, according to S of t is 5t squared. Find the rate of change of the surface of area with respect to time. What are the units for S prime of t? All right, so first we're going to use the same formula, the limit as h goes to 0, and this time we're going to do S of t plus h minus S of t all over h. So again, I like to write out S of t plus h. You don't have to do this, but it helps me. I like to do all my work on the side so I don't make the equation so confusing. But again, that's my prerogative. If you don't like doing it that way, you don't have to. So we'll FOIL out t plus h, and we get 5 times t squared plus 2th plus h squared. Don't forget, I'll just mention this one more time, but don't forget that when you have t plus h squared, it's t plus h times t plus h. So don't forget that that is actually a quadratic and you have to FOIL each piece. So we have 5t squared plus 10th plus 5h squared, and then S of t. All right, so let's take our limit formula. The limit as h goes to 0 of 5t squared plus 10th plus 5h squared minus 5t squared all over h. And now my 5t squareds will cancel. And I have my limit as h goes to 0 of 10th plus 5h squared all over h. I can factor my h out. So the limit as h goes to 0 of h times 10t plus 5h all over h. I can cancel the two h's, and then I have my limit as h goes to 0 of 10t plus 5h. I substitute in the 0 for h, and that piece goes away, and I'm just left with 10t. Now let's talk about the units on S prime. So S prime of t, or the derivative with respect to t, is 10t. So our original function is in square meters. So we're in meters squared, and then we're taking the derivative with respect to time, or we're dividing by time, which is by seconds. So our units are meters squared per second. Example 4 on page 174 asks us to find the derivative of f of x equals x cubed minus 1. Then to graph both of them on the same set of coordinates. I'm going to sketch the graph over here to the left, but I would definitely recommend actually graphing it on your graphing calculator. So I'll walk you through that when we're done with the problem. So first step I like to do is do f of x plus h, and we have f of x plus h cubed minus 1. So I have f of x plus h times x squared plus 2xh plus h squared. And then I'm going to FOIL it out again, or distribute one more time, and I get x cubed plus 2x squared h plus xh squared plus hx squared plus 2xh squared plus h cubed. And I can reduce or simplify that by combining some like terms. I have x cubed plus 3x squared h plus 3xh squared plus h cubed. And f of x is just x cubed minus 1. So now we can plug it into the limit as h goes to 0, f of x plus h, or x cubed plus 3x squared h plus 3xh squared plus h cubed minus x cubed minus 1 all over h. Again, we have the limit as h goes to 0 of x cubed plus 3x squared h plus 3xh squared plus h cubed, and then I'm going to distribute this minus sign to each piece, minus x cubed plus 1 all over h. Now this is a great example. I know right away I've made a mistake because I have a positive 1 right here, and I have no way to cancel that positive 1. And when I look back on my work, I see I had a minus 1 that I forgot to write down. So this is exactly the point where I'm saying, if things don't cancel, I made a mistake. So let's go back and fix that mistake. I should have a minus 1 at the end here, a minus 1 at the end there, squeeze a little minus 1 in there, squeeze a little minus 1 in there. Now I can cancel. My x cubes cancel with my x cubes, minus x cubed, positive x cubed, minus 1, positive 1, and I'm left with the limit as h goes to 0 of 3x squared h plus 3x h squared plus h cubed all over h. My next step is going to be to factor out the h. So it's the limit as h goes to 0 of h times 3x squared plus 3xh plus h squared all over h. I'll cancel out the h's in the numerator and the denominator, and we have the limit as h goes to 0 of 3x squared plus 3xh plus h squared. I can substitute my h now, and this piece will go away, and this piece will go away, and I get my derivative to be 3x squared. So f prime of x is 3x squared. Now let's go to the graphing. It's not going to be a perfect graph because it's kind of a small graph that I've made here. Let's see, maybe if I make this to 1 and 2, negative 1, negative 2. So x cubed minus 1 is going to look a little bit, let's see, something like that, and like that. And then 3x squared is going to be a wide parabola. Something like that. Now let's talk about how to do this on your graphing calculator. I first want you to touch the y equals button at the top of the screen. So at the bottom of the screen, but at the top of the keyboard. You're going to hit y equals, and then you're going to put into y1 x cubed minus 1, and into y2 3x squared. When you have that complete, you're going to hit the graph button, and you'll be able to see a much prettier picture of this on your graphing calculator screen. What's important to note about this is that the graph of the function does not look like the graph of the derivative. They are not similar. They're related to each other, but they are not the same. Now let's talk about some instances where a function has no derivative. Here, we have something called a corner. It's when the limit as x goes to c from the left exists, and the limit as x goes to c from the right exists, but they're not equal. This happens in, for example, in the absolute value function. Next, we have when one-sided limits are both infinite and both equal infinity or negative infinity. When this happens, the graph has vertical tangent lines. So as you can see, an example of that is a cubed root function. And then another way is when both limits are infinite, but one equals positive infinity and the other equals negative infinity. That's called a cusp. This happens when we have a vertical tangent line at the point. One example of that happening is the function x to the 2/3. So this one was x, the cubed root of x, and this one was absolute value of x. It's not necessarily important that you remember cusps and corners. What is important is that you remember that the derivative does not exist at those points. All right, let's take a look at example 6 on page 176. They've given us a piecewise defined function. F of x is negative 2x squared plus 4 when x doesn't equal 2, and x squared plus 1 when x does equal 2. And it asks us to find f prime of 1. More specifically, determine if f prime of 1 exists. So we're going to take the limit from either direction and see what happens. And now I'm about to start the problem. I noticed that I made a mistake here. This should be if x is less than 1, and this should be if x is greater than or equal to 1. All right, now let's take a look at the limit for continuity. So the limit as x goes to 1 from the left, we're going to be using the first function of negative 2x squared plus 4. We get negative 2 times 1 squared plus 4. It's just 2. And then the limit as x goes to 1 from the right of x squared plus 1, or 1 squared plus 1, is also 2. So yes, the function is continuous. If the function was not continuous, I could stop right there and know the derivative definitely does not exist. But since it is continuous, we're going to move on and take the derivative from each direction. So let's start with the limit as x goes to 1 from the left. We have f of x minus f of 1 over x minus 1. Notice I switched back to the other limit formula for the derivative because I'm given a specific point. It's, again, a little bit quicker and easier to use this formula when you're given a point, but there's no reason you can't use the x plus h formula also. All right, so the limit as x goes to 1 from the left of negative 2x squared plus 4, and then I've already found f of 1, which is minus 2, over x minus 1. The limit as x goes to 1, negative 2 from the left, negative 2x squared plus 2 over x minus 1. And then let's factor out a negative 2. So we have the limit as x goes to 1 from the left, negative 2x squared minus 1 over x minus 1, which is the limit as x goes to 1 from the left, negative 2 times x minus 1, x plus 1, all over x minus 1. I can cancel my x minus 1s, and I'll be able to plug into my limit now. The limit as x goes to 1 from the left, negative 2 times x plus 1, negative 2, 1 plus 1, negative 4. So from the left, my limit is negative 4. From the left, my derivative is negative 4. Let's take a look at the limit from the right. The limit as x goes to 1 from the right of f of x minus f of 1. So x squared plus 1 minus, I know that f of 1 is 2, all over x minus 1. So I have the limit as x goes to 1 from the right of x squared minus 1 over x minus 1, or the limit as x goes to 1 of x minus 1 over x plus 1, all over x minus 1. My x minus 1's cancel, and I get the limit as x goes to 1 of x plus 1. Now my derivative from the right is going to be 1 plus 1, or 2. And since 2 does not equal negative 4, f prime of x does not exist. Example 7 on page 176 asks us to show that x minus 2 to the 4/5 has no derivative at x equals 2. Before I start, just like in the previous problem I had to find that it was continuous, I need to make sure that 2 is part of the domain. So first let's take a look at what f of 2 is. So I have 2 minus 2 to the 4/5, which is 0 to the 4/5, which is 0, so that's good. At least we know it exists. Now we have to take the derivative from either side. So we'll take the limit as x goes to 2 from the left of f of x minus f of 2, all over x minus 2. All right, so that's going to be the limit as x goes to 2 from the left of x minus 2 to the 4/5 minus 0 over x minus 2. So we have the limit as x goes to 2 from the left of x minus 2 to the 4/5 over x minus 2. Now, I have an x minus 2 and an x minus 2. This is to the first, or I can think about it to the 5/5, and the numerator is to the 4/5. So when I subtract my exponents, I'm going to be left with a 1/5 in the denominator. So the limit as x goes to 2 from the left of 1 over x minus 2 to the 1/5. And now I'm going to think about what happens as we get really close to 2 from the left. And if you think about it, or you graph it, or you look back in your notes, hopefully you're going to see that we're going to approach negative infinity because we're coming from the left in the denominator. Now let's go as x goes to 2 from the right. Same, f of x minus f of 2 all over x minus 2. We're going to have a similar situation for our limit as x goes to 2 from the right, x minus 2 to the 4/5 minus 0 over x minus 2. When I reduce that, I'm going to get something very similar as before, but this time we're going to approach 2 from the right, 1 over x minus 2 to the 1/5. And since we're coming from the right this time, we'll see that we go to positive infinity. And since negative infinity and positive infinity are not the same, f prime of 2 does not exist. Now let's talk about how differentiability and continuity are connected. We have a theorem that tells us if a function f has a derivative at a number c, then f is continuous at c. What this means is the limit as x goes to c of f of x is the same as f of c. There's a more detailed proof on page 177 that you're welcome to follow. A corollary to this is if a function f is discontinuous at a number c, then there is no derivative. This is really important. It's why we always check the continuity before we look at the derivative, because if a function is discontinuous, the derivative does not exist. Differentiability implies continuity, but continuity does not imply differentiability. Just because a function is continuous does not necessarily mean that it is therefore differentiable. Example 9 on page 178 asks us to determine if the Heaviside function u0 of t equals 0 when t is less than 0 and 1 when t is greater than 0 has a derivative at 0. So again, first we check the continuity. We look at the limit as t goes to 0 from the left of u0 of t, and we see that from the left we approach 0. Now we look at the limit as u goes to 0 from the right of u0 of t, and from the right we see we approach 1. And since the function is not continuous, then the function is also not differentiable, or the derivative u0 of 0 does not exist.